Now it's going to be relatively easy to differentiate after I'm done. Okay, let's tackle it. Let's see. This 4, in other words, this is the same as x minus 3 to the 4th plus the natural log of x squared plus 1 minus the natural log of 2x plus 5 to the 3rd. See what I've done there?
Yeah.
And then that becomes 1/5 times 4 natural log of x minus 3 plus natural log of x squared plus 1 minus 3 natural log of 2x plus 5. And on the left side of the equation, I have 1 over y dy dx. And if I want to differentiate the right side, notice how easy it is to differentiate now. To differentiate this, I'll leave my 1/5 out here for the moment. Well, this is just 4 over x minus 3 plus the derivative of that is 1 over x squared plus 1 times 2x minus 3. The derivative of that is 1 over 2x plus 5. That we're almost done. There's your answer. And if I wanted to leave it as a function of all x, I would go back in and substitute for y that extremely complicated expression that the problem started with. In other words, if I wanted to,
Yeah.
I would substitute this for y, which is what y was equal to. Now, granted, we still end up with an extremely complicated answer. It's always going to be extremely complicated. There's no way around that. But I was able to do this derivative in 5 minutes instead of 30 minutes by taking the natural log of both sides in the first place. In other words, what's difficult about differentiation is when we have a times b divided by c. Well, once I make the natural log of that, that's equal to the natural log of a plus the natural log of b minus the natural log of c. Each of these is very easy to differentiate. We don't have any product rules to apply. We don't have quotient rules to apply. So it's much easier differentiating sums and differences than it is products and quotients. And that's where taking the natural log of both sides is very helpful. You end up changing all of your products and quotients into sums and differences, and then it's very easy to differentiate those. All right, now, see there, I don't know whether I really should have spent that much time on that. If that's not going to be on your quiz,
Well,
I tell you,
looking over it, the only thing in here that looks like I don't know, but not 100% sure on, is piecewise functions and derivatives.
Okay. Piecewise functions and derivatives have to be differentiated in pieces because you can't differentiate across a discontinuity. So if I give you this function here, the only way I could differentiate that is in 2 places, from there to there, and then again from there to there. There's no way I can differentiate across that discontinuity. And same thing with absolute value functions. If I give you this and say find dy dx, well, here's what that looks like. I cannot differentiate across that point. That is called a corner or a cusp. And you can't differentiate at corners and cusps. The only thing I can do is differentiate this and come up with -1 between negative infinity and 0, and +1 between 0 and positive infinity. And that's the slope. Slope's -1 there, +1 there. All right, let me, how about the linearization? If I said find the square root of 4.1, could you do it using the linearization of that function?
I don't think I could.
Let's go through one of these. These are, you're almost certainly going to have a problem on that. Okay, so where the linearization is useful is if you're trying to evaluate a function close to a point. So our basic function there was this. And if I want the linearization of this function at x equal 4, there's a nice tabular way for doing this. The tabular way for doing this is, well, first of all, on the left side, I'm going to say f of x equals square root of x. That's the function. Then I'm going to find f prime of x. What's f prime of x?
1/2 x to the -1/2.
And then over here on the right, I'm going to write f of 4. That's 2. And then I'm going to write f prime of 4. Well, what's f prime of 4?
0.
No, we're going to substitute 4 in to this function right here.
Yeah. Or,
So it'd be 1/8.
yeah.
In other words, it would be 1/2 times 1 over the square root of 4.
Yeah.
It's 2, excuse me, it's going to be 1/4, not 1/8. Okay, so now the linearization of x, written like that, is equal to that plus that times x minus 4. And there is the linearization of f of x equaling root x at x minus 4. Now, what is the linearization good for? Well, the first question I asked you was what the square root of 4.1 was. This will tell us. Because we are so close to 4, the linearization of this should give us an excellent approximation of that answer. And x is going to be 4.1. So it's going to be 2 plus 1/4 of 4.1 minus 4, which is 0.1. So that is 2.025. And if you look up in a calculator what the square root of 4.1 is, it's like 2.0249. In other words, that is an excellent approximation for coming up with the square root of numbers close to 4. Now, if I tried to use this for the square root of 7, it's not going to give me a very good answer. So you use the linearization to calculate, approximate values for functions as long as you're close to the number that it is centered at. But this technique that I used here is worth learning because it took me a long time to learn it. I never really learned it until I started learning about Taylor series. And in a Taylor series, you don't stop with the first derivative. You keep going. A Taylor series has infinite derivatives. In other words, the next thing over here would be the second derivative, and then the second derivative evaluated at 4, and then I would add that second derivative times x minus 4 squared. So every term increases the accuracy of your approximation. But Taylor series are much more complicated. The linearization of a function is basically the first two terms of the Taylor series. And that's made it easier for me to remember it. When I had to learn it as the linearization of a function, it was very difficult to remember this method. But once I memorized the method for doing Taylor series, this became easy because this is just the first two steps of a Taylor series. So the secret to the linearization of a function, no matter what it is, if I said, let's do this one, is you take the first derivative, so you end up with what the function is, what the first derivative is, and then you evaluate both of those at the number that it's centered at. And then the final linearization of x is f of a plus f prime of a times x minus a. There's the linearization formula that you need to memorize. And with every problem that you have to do, you have to figure out what f of a is and what f prime of a is in order to come up with the answer.
I could see how that would be helpful. Just she recently gave me a practice test for chapter 1 that I'm looking through.
Do you have a problem do you have one of those problems? Let's do it if it's a linear.
Yeah. There's one I was looking through. I was going to give it to you next week after she graded it, so I did along with this one. I'm not sure how to do.
Okay.
It's find the value of c such that f of x is equal to, and it's a piecewise function, c of x squared minus 7 if x is less than or equal to 3. And then the other one is c of x minus 3 if x is greater than 3. And then it's so it's find the value of c such that that is continuous on R.
Okay, let's draw a model.
Yeah.
When x is greater than 3, this thing is linear. And it would go through the y-intercept if it got all the way over to there. And it has some slope that is c.
Yes.
Okay? To the left of 3, and this is an open circle, to the left of 3, this is a quadratic that has been shifted up from minus 7. In other words, it's a quadratic that does something like this. You with me?
Yes.
So we have to figure out what c would put this on top of that, because that's the only way it's made continuous.
That makes more sense.
Okay, so now how are we going to do this? What if we took the derivative of that part of the function? Hold on a second. Let me think about this. This is kind of a tricky problem.
Yes.
Well, let's see. Don't we need cx squared minus 7 to be equal to cx minus 3. It might be as simple as that. I think it is. However, that's two variables, one equation. That would not appear to be a calculus problem. However, if we look at it and try to solve it as a calculus problem, f prime of x is equal to cx, and that f prime, and this f prime of x is equal to c. One represents the slope there, and the other represents that slope. So right offhand, I don't quite get why the slopes would help us here.
This test was thrown at me this morning, and I was looking through it as we were talking, and I came across that one, and
yeah,
I have no idea what she wants me to do there.
Well, I'm thinking here for a moment. Let's see. Can we figure out the intercepts on this top function? We know it's going to have two x-intercepts. Does that do us any good? Not really. In other words, we want to know the picture that must be the case is this. And in order for us to get that picture, C would have to be narrow enough. In other words, if I were to draw a parabola with a different value of C, it wouldn't intersect at that point. So, what does that tell us? That tells us the reason it intersects is because cx squared minus 7 is equal to cx minus 3. Why can we not solve that? Let's see, if I bring the cx over, well, we might be able to solve this. Let's bring everything over to the left side. We have cx squared minus cx minus 4 equals 0. I can, wow. If I factor this out and try to complete the square, does that answer it? No, it doesn't. Why can't we solve that for C? Can we solve that for C?
Well, we didn't get C in terms of X, wouldn't we?
No, we would get, in other words, if C were 1, there would only be 2 solutions for this.
Yeah.
If C were 2, there would still only be 2 solutions.
Mm-hmm.
What if we have tried, what if we say that x equals minus b, which is C, plus or minus the square root of C squared minus 4a, which is C, times C, which is minus 4, all over 2C. It doesn't solve for C. Wow. It's clear to me that we should be able to solve this because we know where this function goes, right? In other words, we don't know the slope of this part, but we know this point right here. This point has to be in both places. What point is that? That is x is equal to 3. Here we go. Substitute 3 for x and solve this equation, and we've got our value for C.
So we would...
And in fact, let's go back to how I had written it originally. Let's just try to solve this. This is probably going to be easier than solving this quadratic. In other words, I know that this is equal to that, but only at x equal 3, correct?
Yes.
So that's all I have to solve.
3?
Yeah, so I'm going to plug in 3 for x, and I get 9c minus 7 equals 3c minus 3. So now I have 6c equals 4, c equals 2/3. There's your answer. And that it doesn't require calculus at all. What it's merely saying is that at this point, x equal 3, both of these functions have to have the same value right there. And that has to equal that. Plugging in 3 for x allows me to solve for C.
That was... Well, that seems easy now in hindsight, but originally I looked at this question and it confused me.
Yeah, well that was a tough one, especially if you're thinking you need to use calculus to solve it. And it's not a calculus problem at all.
I wonder why she has it on the calculus test.
Yeah, I don't know. But I'm 99% sure that that was the correct answer. And we could even prove it. I could put both functions into Wolfram alpha and make sure that it's continuous. But let's go on to something else. You have any other problems kind of like that came off the quiz that you're not sure how to do?
It was thrown at me recently, so let me just look through here real quick.
Okay.
I haven't looked through the whole thing yet. I haven't had it very long. Yeah, so the following is true. Find the equation of tangent line of the curve, the indicated point. So there's everything.
Implicit differentiation. We probably should cover some of those also.
Yeah, that is going to be on the test.
Implicit differentiation, or?
Yeah, that is going to be. Yeah.
Well, let me give you one. Let me give you one to implicitly. I want you to implicitly differentiate this, and this is not easily done with explicit differentiation. In other words, implicit differentiation is needed in order to differentiate this.
So we would just go 2x, right?
Right.
We're differentiating, so yeah, 2x.
Right. We're trying to find dy dx. I should have said that, because it's not just a question of differentiating it, it's differentiating it with respect to the variable x. Okay.
And then the next term, we have to product rule that, don't we?
Correct. So apply the product rule to that quantity. Let's put parentheses around it.
So we would get y for the first one, right?
Right.
As the x turns to a 1, we just get a y. And then the second term, we would get x dy dx.
Yes.
And then plus 2y dy dx.
Right.
Equals 0.
Okay. Now what? This is kind of the tricky part, actually, in most of these problems.
This is more the algebra, though, isn't it?
Right. It's just complicated algebra.
Yeah. So, I'd move the dy dx's to the right side of the other side of the equation, so we would have...
Okay. So I got 2x minus y on the left, and on the right I'm going to have x dy dx minus 2y dy dx. Okay?
Now we got to move over the x and the 2y somehow.
Here's the, yeah, this is the trickiest part of this solution, is what to do at this point.
Because just dividing by that wouldn't work well.
No, but think of factoring out the dy dx.
Yeah, and then, so we would get, and then we could divide by the
Exactly.
x minus 2y.
And that's your answer. And we have no problems having answers that have x and y as the answer.
Yeah.
I mean, since we don't have a value for y, we can't actually solve this for y. So we can't even go back in and substitute for y.
Yeah.
In other words, this has to be our final answer. Some problems you would have a choice. You would know what y was. You know, when we started out and we had that problem there, we knew what y was. So when we got an answer in y, I was able to substitute this back in for it. Well, we can't here, and we don't need to. There's nothing wrong with having your answers in both x and y. And you're implicitly differentiating. This particular function happens to be the function of a ellipsoid that's been rotated, something like that. And so if I wanted to know the slope at any point on the curve, give me a point, 3, 3, plug it in for here, I know the exact slope at that point. I want to know the slope right there. Give me minus 2, 2. Plug it in. You get the slope there. So having your dy dx be a function of x and y is not bad because you're frequently evaluating it at an xy coordinate.
That makes sense.
Okay. Let's see here. I'm looking backwards from the end of chapter 4, going back. So you're comfortable with implicit differentiation, right?
Yeah.
You were able to do that problem, so that's pretty good.
It's more just the remembering the algebra.
Right. Well, let's do some difficult differentiation. In fact, yeah, I'm looking at some exercises in the back of one of these. Let's just make sure you can differentiate most functions. It's y prime equal.
Okay, so or y prime sine squared y prime. So
There's a couple of ways you could do this. If you're having difficulty figuring out how to do this, let's use substitution to tell us what's the inside and what's the outside.
I'm going to say that step 1 would be to put the 3x minus 2 as a u.
So now the problem becomes this.
Okay, so I think what I would do would be 2 cosine u.
Okay, let's go one step further here. We've got two insides here. The 3x minus 2 is an inside, and I'm going to let z equal sine x, or actually sine u. So what I really have here is y equals z squared, right?
Yes.
So if I take the derivative of the outside, I get 2z, and then I got to take dy dz, and then I got to take du dz, or du dx, and dy dx. Excuse me. So, in other words, where we get to, by the time we've done all that, is y prime is going to be equal to 2 sine of 3x minus 2. That's the derivative of the outside.
Yeah.
One inside is sine u, so we need to multiply it by the derivative of that, so that's cosine x. And the other inside is that, so we need to multiply it by du dx, which is 3.
3.
So that's how we would do that. You have to apply the chain rule twice. Let's do more of those. It seems like this would be the best thing for you is going to be to drill on these difficult chain rule ones. Let me find another one. Again we have two insides.
Yeah.
We have that is one inside, and that's another inside. So let's start by taking the derivative of the outside.
Which would just be, what, 2 times that quantity?
Yes, exactly. In other words, your first step is always just applying usually the power rule and leaving the quantity unchanged. But I know I have to multiply it by the derivative of the inside. What's the derivative of this inside?
1, not the 1 goes away, so just negative sine of 2x.
Correct. And now one more inside is the derivative of that inside.
Which is 2.
And there's your answer.
It's just a matter of determining the insides. And then
Yeah, exactly. And usually, well, let's do some more. Let me find some that have some tough insides. Here's one.
that looks like fun.
So let's do the first step.
So just 3 the quantity squared.
And the first big inside.
So, because we have the cosine squared, does that just make the first big inside 2 cosine of 7x?
Yes, and then we have 2 little insides. We have that's one more inside and that's one more inside.
One more inside.
So yes. In other words, so the derivative of this inside is 2 cosine of 7x. That's the derivative of the long horizontal line. Well, it's not the full derivative. We're still working on it.
Yeah.
And the first inside would be cosine 7x. The derivative of that is negative sine 7x. And then the derivative of that inside, 7. So there's your final answer.
Okay.
Okay?
That makes sense now.
Yeah, you just kind of, I don't
Work
know.
through the
I don't
trig
know
function.
if it's easier to do by using letters as variables or not. Sometimes that makes it a little more confusing to me.
I think that my issue with the first one was understanding the fact that because it's like it was sine squared, that the sine itself that needed was 2 insides there because of that.
Right. If you can do these two problems here, and this problem, if you can do both of these problems, it's tremendously useful because these two problems teach you what the inside is. In other words, in this first problem, the inside is sine x, so that we have u squared. The second problem, the inside is x squared, so that we have the sine of u.
Yeah.
Okay, and then you're going to have to apply the chain rule in each case. But this probably is the most difficult part of the chain rules, I think, is the trig function.
Yeah. I also didn't have a great teacher for trig, so it took a while for me to understand trig functions. I understand them now, but I had issues with them for quite a while.
Yeah, I don't know if you're going to get anything that might look like this or not, but let's take a quick look at it. I guess this is pretty straightforward. So what's the answer if we do it using the chain rule?
So we get the outside first just becomes negative sine. Oh no, yeah, negative sine of the quantity. And then the inside we get what do we do with pi? We just
Negative 3. In other words, we're trying to get ds dt here.
yeah.
Okay? So that's one way to do it. Pretty straightforward.
Yeah.
But notice another way to do it. Cosine of pi over 2 minus 3t is the same as the sine of 3t. That's one of those trig cofunction relationships, that the sine of x is equal to the cosine of 90 degrees minus x.
Yeah.
Likewise, the cosine of x is equal to the sine of 90 degrees minus x. So if I turn this into this function first, it becomes much easier. Derivative of sine is cosine of 3t times 3. Now, why didn't I get the same thing? I did. Because now I can go back and change that into cosine of 3t.
Yeah.
All right. So that, you didn't really need that trig relationship, but it helped, made it a little bit easier to use it. See if I can find some others here. What's this one?
So first I would have to rewrite that as to the 1/2. And then we would do the outside first, so we get 1/2 tan 5x to the negative 1/2. And then the inside we'd get secant squared of 5x.
Yep.
And then we would get 5.
Good. Good. And that's it. Okay. So you seem pretty good with the chain rule, even double or triple chain rule. Let's go back and let me see if I can find something else to challenge you here. Here's kind of a word problem that it's worth knowing. Find the slope of the line tangent to the curve y equals sine to the 5th of x at the point x equal pi over 3.
So then wouldn't you just differentiate it and then put in pi over 3?
Yeah. Yeah, so that's not hard at all. Yeah. Yeah, the derivative of that is 5 sine to the 4th of x cosine x, and then just evaluate it at pi over 3. So, all right.
Okay, so I think next week will tell better, but I think I'm good for chapters 1 through 3.
Okay,
Right.
sounds good. Let me just look at a few other things here. How much do you have to memorize? Do you have to memorize the derivatives of the inverse trig functions, or are you going to be able to call on a table?
She hasn't told me yet. She said that she is currently still building the test, but that she would tell me as soon as she knows.
Well, let's just go through the 3 main inverse trig functions. What is the derivative of inverse tangent? You want to memorize these 3, the 3 we're going to go over right now. I start out with tangent because it's the easiest one.
With that, I don't know.
It's right there.
I don't have it memorized.
Okay.
1 over John.
Okay. If y is equal to inverse sine, this is the other one, excuse me. You want to memorize these 3. Then y prime is equal to similar, only it's 1 over the square root of 1 minus x squared. And then the third one is y equal inverse secant. And that y prime is, remember this?
Yeah, I think I do. Is that one the absolute value of x, square root of x squared minus 1?
Yes.
Yeah, I do remember that one.
Okay. So that's inverse tangent, inverse sine, and inverse secant. So what would inverse cotangent, the derivative of cotangent, be?
Just negative 1.
The negative of each of these.
Yeah.
In other words, the derivatives of the cofunction inverses are the negatives of this one. cotangent would be minus 1 over 1 plus x squared. Cosine would be minus 1 over square root of 1 minus x squared. And cosecant would be minus 1 over that. So if you memorize these three, you always can figure out the other three.
Okay.
And what's kind of interesting to note is that when you take the derivative of inverse tangent, notice you get a polynomial. You do not get a trig function.
Yeah.
You take the derivative of trig functions, you get other trig functions. But when you take the derivative of an inverse trig function, you do not. And that actually becomes pretty important when you go to integrate some polynomials. In other words, if you're integrating this, it's nice to see that that's the derivative of tangent. So the integral of that is inverse tangent.
Yeah.
Even though you wouldn't think of that necessarily when you look at that. But okay. Well, Chase, good luck on this test, and hopefully next time we meet we'll be working on Chapter 4. Or I'm perfectly willing to go over, any ones you missed on this quiz coming up also.
That test will be in 3 weeks. This week she gave me the practice Chapter 1 and 2 test, and she'll grade them for me.
Okay.
So I know what I did wrong on those, so hopefully next week I'll know what I did wrong on Chapters 1 and 2, and we can just go over that and make sure I don't make those mistakes on the real test.
Sounds good.
Okay.
I will talk to you next Saturday at 2.
You too.
All right.
Thank you.
Bye-bye.